Hello students, myself Janil Popat. Let us discuss second video lecture, shear strength of soil. In first part, we have discussed that basic idea of shear strength as well as basic terms, how it is gaining from soil, as well as its graphical representation, as well as normal stresses, shear stresses, Mohr's circle, and some formulas related to that. Let us begin this video lecture with another theory, with Mohr's strength theory. Mohr's strength theory is based on a hypothesis of soil failure. Now, Mohr has a hypothesis that at the time of failure of soil, at failure plane of the soil, the failure shear stress is direct function of normal stress. That means we can write it as tau f, that is shear stress at failure, is function of sigma, that is normal stress. Where another thing which comes in the mind, that at the time where the soil is failing, that stress, that ultimate stress is obviously shear strength of your soil. So we can also write S in place of tau f. So S is equal to function of sigma of normal stress. Now we can also write tau is equal to sigma into 10 beta, because here tau shear stress will be sigma into 10 of beta. Beta is what here? Beta will be angle with the resultant. As in the previous video we have seen that in the Mohr circle, beta was the angle with the resultant. So we can write tau is equal to sigma into 10 beta. Same way, now at the time of failure, tau will be maximum, or we can say shear strength of soil. So we can write it as, same way at the time of failure we can write beta as phi, or beta as angle of obliquity. Beta is known as angle of obliquity. So I am writing the same thing here. Tau is equal to sigma 10 phi, and S shear strength of soil is equal to sigma 10 phi. So Mohr has derived some formula from the failure envelope of soils. So here you can see two graphs having tau versus sigma. Now in the first graph you can see Mohr's circle, number of Mohr's circle, and green line is showing Mohr's failure envelope. So many type of soils are tested, are given pressure, are given failure even, and one failure envelope is prepared from that, and from that hypothesis Mohr's strength theory is derived. Same goes for another graph which is showing point of tangency. Point of tangency, this graph is trying to show that if this is your Mohr circle, the point of tangency of Mohr's failure envelope will show failure of this particular soil. So this is all about Mohr's strength theory. Let us move further to another theory, which is Mohr-Coulomb strength theory. In investigations, Coulomb found out that at the time of failure, shearing strength of soil will be divided in two components. From two components, one component will be independent of normal stresses applied to that, and that component is having intrinsic cohesion, or we can say apparent cohesion. And another component, namely we can say frictional resistance, will be dependent on normal stress which is applied on that soil. So he gave an equation empirically, that is S is equal to C plus sigma 10 phi. Here one component is cohesion and second one is frictional resistance. So we can plot a graph from these lines. S is equal to C plus sigma tan phi. Here C is constant and it is not dependent on applied normal stress. So we can see this graph. Here C is constant, phi is angle of internal friction, and it is having a line which is given as name as S is equal to C plus sigma tan phi. Now it will depend on your type of soil, how the soil is behaving. For let us say phi soil. For phi soil, which is also known as cohesion less soil, which is having C cohesion 0, it will give you chart like this, tau versus phi, where the cohesion is 0, so there is no constant height of the graph. So it is directly going like this, and here S shear strength will not depend on C, it will only depend on sigma tan phi. If your soil type is C soil, or we can also say this cohesive soil, so there will be no friction if it is a pure cohesive soil. So the graph will stay constant because cohesion, the first component, it is not dependent upon applied normal stress. So the graph will go in a straight linear line manner. So we can see C as some constant and phi as 0. So S will be directly is equal to cohesion. So cohesion will govern its shear strength. It is very simpler. But if your soil is C5 type of soil, I mean mixture of cohesion less and cohesive soil, the graph will remain like I have explained in the first place. It will be having C as well as phi. So S is equal to C plus sigma tan phi. So Mohr-Coulomb strength theory was phenomenal at that time, and it gave very revolutionary outcomes at that time. Let us move to new theory, which is modified Mohr-Coulomb's theory. So apparently it looks like at the time of failure, shearing strength of soil is dependent upon applied normal stress. But according to Terzaghi and our understanding from the chapter soil water, we can say that the normal stress is governed by effective stress, not the total stress. So we can say that the shear strength will be governed by effective stress, not the normal stress. So we can take sigma dash is equal to sigma minus u from the chapter soil water. If we remember that effective stress is equal to total stress minus neutral stress, and S can be written as modified by Terzaghi's theory. S is equal to C dash plus sigma dash tan phi dash. And here C dash means effective cohesion, phi dash that is effective angle of friction, and sigma dash that is sigma minus u, which is normal stress minus neutral stress, will be effective normal stress. Now let us understand some basic experimental situations. Shear tests based on drainage conditions. So shear tests are defined by different drainage conditions like UU test, which is unconsolidated undrained test. In this test, UU test, no moisture is permitted in the first stage. First stage means consolidation stage, so it is called unconsolidated. As well as it is not permitted, moisture is not permitted in the even second stage, where the specimen will be sheared. So this test is called as unconsolidated undrained test. It is generally preferred for clays, and it is also known as Q test. Q means quick test here, as it will give results in few minutes. Second one is CU test, that is consolidated undrained test. Now, in these tests, in CU test, first stage will be consolidation stage, and in that stage, moisture is allowed, or we can say water is allowed to touch that. But in the second stage, where the specimen is being sheared, there will be no moisture allowed. It is R test, which is in between Q and S. It is also known as a rapid test, and it is generally used for sudden drawdown cases. I mean, wherever the drawdown of water is sudden, you have to test with this test. And the third item, according to drainage conditions, is CD test. That is consolidated drainage test. Now, in this stage, in both the stages, consolidation and shear stages, drainage or moisture is allowed. So, it is done throughout the moisture availability. It is giving the results slow, and it is known as S test. It is generally used for checking long-term stability of clays. Let us move to the first test, that is direct shear test. Direct shear test is also known as shear box test. In this box, which is having soil specimen, it is very important to understand and fulfill it properly. Let us understand this experiment. In this figure, you can see an assembly which is showing direct shear test. In this, in the center portion, you can see the blue box is there. Under that, or in that blue box, one soil specimen in the box is kept, and dial gauges and proven ring are applied to that, attached to that. They will give different type of measurements, and we also can apply normal stress as well as shear stress both to this specimen through this test. Let us understand procedure gradually. First step is to attach base plate and box. So you have to attach base plate, one plate of metal with the box. You have to place porous stones and grid plate on the box. So whenever base plate and box is ready, you have to put two porous stone and grid plate both under this. Then you have to wait for that the box and everything should be weighed. Place the specimen in the box. So specimen or your soil which is prepared should be put in the box. Then you have to put again grid plate as well as porous stone on that, and you have to fix a loading pad. Loading pad will do what? It will distribute the load uniformly into the soil. So you have to fix the loading pad, and also upper half with proving ring. So you have to set the box is generally in two parts. In upper part you have to attach proving ring, and in the bottom part you have to mount dial gauge. Then you have to place the weights and apply normal stress. So in this figure you can see a black rod and weights are attached to that. So these weights will provide normal stress to the soil specimen, and it is told to apply horizontal shear at the rate. Do remember the rate, it is very slow, 0.02 mm per minute. You have to apply shear stress and continue up to 20% of the material will be strained. So when the box is strained almost up to 20%, till then you have to apply the shear stress as well as normal stress. Now after getting it strained, you have to take it for water content determination in the lab and repeat the test and record shear forces. So you have to repeat the test with variations in the normal weight or normal stress on that soil specimen, and shear stresses will change. So you will have a graph of values between normal stresses and shear stresses of different specimens. So this is how you will prepare a graph from direct shear test, and that will show us the failure envelope by Mohr. So let us keep our session up to this. We will learn different fundamental experimental fundas of this chapter in the next video. Thank you.